Good afternoon to one and all. Let's start today's session with a keynote address. It's a pleasure for me to introduce the keynote speaker, Padma Shri Chandrakant Pitava. Sri Chandrakant Pitava retired as Distinguished Scientist and Director, Electronics and Instrumentation Group in August 2015 after 45 years of service in Baba Atomic Research Center, BAC, Mumbai. Sri Pitava did his Bachelor of Electrical Engineering from Government Engineering College, Rewa, Madhya Pradesh in 1973, 1 year BARC Training School course in Nuclear Science and Engineering in 1974. Masters of Engineering in Automation from Indian Institute of Science, Bangalore in 1981, and MS in Electronics from University of Southampton, UK in 1986. Sri Pitava made significant contributions to the control system of pressurized heavy water reactors, compact light water reactor, prototype fast breeder reactor, and electron and proton accelerators. He led the team in development of indigenous high temperature neutron detectors, first in the world for the 500 MV prototype fast breeder reactor. He designed and developed servo control system for the 115 ton. He has contributed for many international projects, including Large Hadron Collider of CERN, Geneva. Sri Pitava played key role in many strategic programs, including 1998 Shakti nuclear test at Pokhran and the control system for the nuclear population. Sri Pitava has been conferred several awards, including 6 DAE, Department of Atomic Energy, awards for excellence in science, engineering and technology, and outstanding service awards for the Indian Nuclear Society. He has given 4 years of service extension beyond his normal retirement age of 60 years. Later, he served the Department of Atomic Energy as Narayanamma Fellow for 3 years at ECIL, Hyderabad. In 2017, the President of India conferred Padma Shri on Sri Chandrakant Pitava in recognition of his distinguished service in the field of science and engineering. We are glad to have you here, sir. Thank you for accepting our invitation. Now I request Pitava sir to deliver the keynote address.
Okay, good afternoon. I've been given 40 minutes and let us see how much you get interested into this topic. I will be talking about instrumentation control for nuclear power generating plant. Now, before we go further, let me tell you briefly about the what is nuclear power generating plant? You know the thermal power plant. In that we use coal to generate heat when it is burned. The water is heated, converted into steam, and that steam is used to drive the turbine, steam turbine, on which the shaft we have an alternator which produces electricity which is transmitted and used by industries and the public. Nuclear power generating plant is also works in the same way, except that in thermal power plant we have got boiler where coal is used. Here we use nuclear reactor, and nuclear reactor generates the heat. So rest other parts remain same. Now the question is, how the instrumentation control system for a nuclear power generating plant is different. See, we have got so many process industries, there also we use. And there various parameters are regulated as per requirement. To know why it is slightly different, we must know what is the nuclear reactor. So what is a nuclear reactor? Some of you may be knowing. Let me tell briefly. Nuclear reactor uses fuel like uranium and plutonium and has a neutron source. When neutron from the neutron source is absorbed by the fuel atom, it becomes unstable and breaks into two lighter atoms called fission products. Now this breaking is not like that you take a piece of coal and hammer it and it becomes two pieces. It's the breaking of atom. See, for example, uranium is 92 U235. That is, it has got 92 protons and 235 minus 92 neutrons. So when the neutron is absorbed by the uranium atom, it becomes unstable and breaks into two pieces. This is called fission product. The breaking of fuel atom is called fission. So this is fission reactor. The sum of the mass of the two fission product is less than the mass of the uranium atom. This is because the fission process is also associated with the liberation of 2 or 3 neutrons. So when it breaks, 2 or 3, some fission 2, some in fission 3, neutrons will be freely liberated. It means in those two fission products, 3 neutrons are less. So mass of those two fission products, since number of neutron and protons are different, these are different materials. So those two, the sum of the mass is less than the original uranium. This loss of mass gets converted to energy by the Einstein's relation E is equal to mc square, where m is the difference in mass and c is the velocity of light. This energy is the form of kinetic energy of fission product. Fission product which is produced have got velocity. That is the have kinetic energy. Once the fission reaction has been started in some atom of the uranium by means of an external source, fission can be maintained in other uranium atoms by the neutrons generated in the fission product. Because 2 or 3 neutrons generated, they cause fission of the next other neutrons. Again 2 or 3 neutrons are generated. So once it is started, the fission continues. In a fission reaction of uranium-235, about 210 billion electron volt energy is generated in the form of kinetic energy of fission product. You know EV, electron volt energy, when an electron is accelerated with a voltage of 1 volt. So 210 million electron volt is generated in one fission. This means if all the atoms contained in 1 gram of U-235 undergo fission in one day, 1 megawatt power can be generated. How you will calculate this? Because you know every gram atom has got how many atoms? Now for U-235 gram atom is 235 because U-235. So 235 grams of uranium will have how many atoms? Equal to Avogadro's number 56024 into some 10 raised to 24 atoms. So if all those get fission in one day, you will get 1 megawatt of power. Thus, 1 kilogram of uranium-235 can produce energy equivalent to 2800 tons of coal. It's a very high density source. The kinetic energy of fission fragments get converted into heat when they are stored by the surrounding structure material. This heat is used to convert water into steam. The steam drives the turbine, which is connected to alternator to generate the electricity. So this is how it works. This is pictorially shown uranium atom. You can see this. You can see this uranium atom when neutron is absorbed, it goes into fission product, and 2 or 3 neutrons are generated. This is how it happens. This is the actual nuclear fuel used in 220 megawatts of Indian reactor. This is about 18-inch long, and there are 19 fuel bundles. In this is zirconi material. Zirconi is a metal. Inside there are uranium metals, uranium fuel pellets, small pellets, and this is around 18-inch long. This is how fuel is stacked. What you see, this one is a big vessel. The diameter is around 6 meters and length is also 6 meters. And there are, in 220 megawatt, there are 306 channels. And this fuel bundle goes inside this, and there will be 12 fuel bundles in each. I am talking about 220 megawatt nuclear. This is what is another view. This is actually called calandria, and there are 2 end plates called the end shields, on which this calandria tube is mounted, joined by extrusion. Inside there is a pressure tube. Inside there are fuels. There are 12 fuel bulbs, and here fission occurs. Water goes inside this, gets converted into like this. The pressure of water is 87 kg per centimeter square. And, water temperature is 273 degrees. It remains in liquid form because of the high pressure. And this water is a heavy water, D2O, not H2. This D2O gets heated, transfers its power, heat to light water, H2O, which is goes and drives the turbine, and that turbine connected to alternator. So this is the plant. Here you can see this is the reactor giving a heat. Heavy water becomes hot water. This is the light water. This is steam generator where the water gets converted into steam, generates the turbine, goes to turbine, turbine rotates, and this is alternator, which generates power. And the condenser cooling is by seawater. We have got right now 22 So we have got 22 reactors operating, generating 67,080 megawatt. There are 9 reactors under construction at the moment with capacity of 6,700, and another 12 reactors are planned by 2030 to generate 9,000 megawatt. So by 2030 we will have 43 reactors of 22,480. Now let us come to our topic of instrumentation and control of nuclear power plant. Now there is another thing in the reactors. Say these are the fuels like uranium and plutonium, which are radioactive. Radioactive means it emits the nuclear radiation, alpha, beta, gamma, and neutron is also there. These are harmful to our bodies, is biological things. Alpha, you know, is a helium atom, when it can be stopped by even your skin. But if it goes inside our body through blood or through mouth, it will dissociate the blood and the person will die. There is beta, which is like X-ray. Whenever electron goes from higher energy level to lower energy, this comes out. And gamma, which is generated whenever a nucleus at high excited states comes out to the
lower energy level. This gamma is available in the reactors or various energies, very high energies, and these really will be affecting the human body in various ways. If it's small dose, it may just loss of hair. If it is a large dose, you can get leukemia. Very large dose, instant death also. So, when you design any system in the for the reactors, nuclear reactors, you have to be very careful. It is high reliable, it is safe, and there is no release of nuclear radiation to the public or the environment. Why environment? Because of nuclear, this fission product or any radioactive material falls on the ground, it will be there in grounds, grass, these kettles will eat that grass, and through the milk radiation will come to our body, or if it goes in the water, people eat fish, it will again go to it. So, we have to prevent and we have to ensure that whatever system we design, whether it is instrumentation control or any other systems, in no case the nuclear radiation goes to the public or to environment. That is the major difference. So, it has to be highly reliable. So, each instrumentation control system performing protection, control or related task in nuclear power plant spans all elements from plant sensors to control actuators, includes provisions which facilitates operation, in service testing, online diagnostic and the maintenance task. I will go in detail of this. This is the true for all the process industry also, but online diagnostics and online servicing is important. When instrumentation control system perform functions important to safety, these systems must be demonstrated to be safe and reliable with appropriate degree of confidence. Now, whom we have to demonstrate? We cannot design any system and put in the reactor, we cannot start. There is a independent body called Atomic Energy Regulatory Board. Each design has to be presented to them and make sure that it is safe and reliable. They will ask thousands of questions, you will have to produce lot of documents both for hardware and software, present them, and then there will be thousands of questions, you have to answer them and get satisfied. So, there are codes and guides in writing which every system has to satisfy. So, we know what are the codes and guides, we have to design that way, and from that again they see whether something is missing or not. So, this is the, that is why it is important. Now, in nuclear power plant we classify in 3 systems: IA, IB, IC. Protection system, control system important, and systems important for plant operation, but not directly affecting nuclear system. What is control system? Control system will keep the parameter at a desired level. It can be anything, it can be nuclear power itself, flow, pressure, anything. It will try to keep it at the desired level, whatever is required. Protection system, and it will also, control system will ensure that even under process transients, it should not go to the accident level. What is protection system? Somehow if your power control system has failed, protection system has to come into picture to shut down the reactor. How reactor shut down? You know, neutrons are needed for fission. Just drop some material. There are what is called shutdown rods, which are kept at the top of the reactor, which consist of a neutron absorbing material rods, boron carbide, etc. It is hanged on, it is hanged by a rope, which is a steel rope, which is wound on a drum, and then drum is held at the place by a magnetic clutch. Now, suppose something happens, protection system will de-energize the club, power supply will disconnect it, the rods will fall on gravity and it will absorb the all neutrons, the reactor will shut down. So, that is what is a protection system, and there are other systems which are needed for operation, but not important to safety. So, we follow defense in depth philosophy. First layer, as I told you, is control system, which maintains plant parameters within set limit, prevents operation transients leading to accident conditions, and minimize need for actuation of protection system. It should be very reliable. Although you know there is a protection system to help you to shut down the reactor, but you should not ask for action of control system should be so reliable, it unnecessarily does not ask for actuation of protection system. Why? because suppose your plant is operating at 1000 megawatt and you shut down it, you are coming to very low levels, almost 0. What will happen? There will be so much thermal shocks that the mechanical material will undergo those stresses, and if it happens many times, it may fail because of fatigue and all that. So, you have to make sure your control system is highly reliable. Second layer is a reactor setback or reactor step back. What is that? Suppose some parameter control system is trying to control, but some parameter is going beyond certain limit, then you give reactor setback, that is reactor power is reduced at a certain rate till the parameter comes to its within limits, or you give a step back, suddenly from 100% to 60% power is brought and then seen whether it parameter comes, otherwise finally shut down. And third layer is a protection system. It assures safe shutdown of reactor, that is the rods drop. If you need, you know that there are 24 shut off rods in reactors. So, we know 18 shut off rods will be doing the job, but we provide extra because if some rod gets stuck because of some reason, it should not lead to any. So, we assure safe shutdown reactor. There is a secondary shutdown also. It is, we do not only depend on this. Suppose because of, if it does not actuate within 1 second of the 1.2 seconds of some signal giving, then there is a liquid gadolinium nitrate which is goes because of gravity to this inside the reactor to absorb the neutrons. Remove heat from the core. There has to be continuous cooling, because even if you shut down, 0.6% of power is still there. Suppose you are working at 1000 megawatt and you shut down, 6 megawatt of power still be generated by decay heat, because there are fission products which are giving out the reaction nuclear radiation which generates heat inside the reactor. So, still 6 megawatt will be there for few days. So, you have to continuously provide the cooling. If cooling is not available, the fuel may melt, accident may happen, all those things are possible. And if you say I think Fukushima incident, if you know, in Japan, accident had happened. That was because of the tsunami. The tsunami happens whenever there is a earthquake and something is happening. Plates moves vertically. So, whole water, the sea water goes up and tsunami gets generated. And they had put the walls around that, and they had calculated that in any worst case scenario, the tsunami will not go beyond some 10 or 11 meters, but it was so strong that it crossed and went. As soon as happens, all reactors have got facility that as soon as some earthquake or something is there, reactor is shut down immediately. It was shut down, but water went inside, and then when the cooling has to start, all the water went and all diesel generators at other things were submerged in water. So, it was not able to provide the cooling. Also, this there was an alternator which failed, and hydrogen is used for that cooling of the alternator. And when hydrogen, some more than 4%, 4 to 8% hydrogen mixed with the oxygen, it becomes explosive. Although hydrogen oxygen makes water, but 4 to 8% is very dangerous, and that caused fire, and then it was a major accident. So, removal of heat from the core becomes very important. Also, contain radioactivity under accident condition. If suppose accident happens, you have to contain radioactivity. Now, what's the worst case accident is that in the primary coolant circuit, heavy water, the pipe breaks and the water leaks. Although we design those pipes to some standard, I do not know, mechanical thing, but it is called some class A of ASME and something like that, where it should not fail. But suppose it fails and water gets leaked, that may lead to the melting of fuel and release of radioactivity. So, we have got a stored water at the tap, which by gravity will try to cool for some time, and then it finally it may go down. There is a sump, and that the water gets accumulated in the basement, that is again pumped back. But it may happen that it is not sufficient, lot of steam gets generated, lot of this and there. So, whole reactor is contained in a building called containment building, that even if everything is evaporated and the pressure generated, it should be able to take that pressure and should not nothing should get related, and then we have got another second containment. So, reactors are very safe. Now, what are the design requirements of a safety critical control systems? Maintain plant parameters within safe limits, that is for any process industry also. High reliability, safety, security and availability. I told you reliability, safety and security. Security means nothing should be, no one should play with the software, your software. So, these are embedded systems, put in EPROMs and all that, it is not a PC based systems. And there also anything you want to attend, there is a key switch plus password, two things are needed at different levels. Minimization error by avoiding complex designs, software has to be as simple as possible, so that it can be verified and validated by the independent agency. Fail safe output. Fail safe output, even if a control system fails, the output should go in a way that it is safe for the plant. I gave an example of shut off rod, a magnetic clutch. Suppose power supply fails, what will happen? Magnetic clutch will get de-energized, rods will go in. So, if it failure leads to the shutdown of the reactor. Similarly, in control systems flow, you can have the fail safe condition, in some case maybe that valve is fully open when it fails. So, we design the control system that even when it fails, it gets that signal to open it, keep it in that particular condition. Single failure criteria. No single failure anywhere in the component or system or anywhere should lead to failure of the control system. So, we do not use a single control systems, we use triplicated control systems. There are 3 systems, there are 3 sensors. For suppose it is a pressure, you will have 3 pressure sensors coming to this thing. In each system, 3 systems, we will have 3 boards. Suppose there is an analog input, it will not be one analog input, there will be 3 analog input, and those 3 sensors will come to this, again 3 sensors will go to this, again 3 sensors will go to triplicated systems. And then you do median selection. Suppose you are measuring a flow, it is in one sensor is giving 10, another is giving 10.1, you is giving 10.3, you see the median central value. That value is used for calculation, and when output is generated, again there is a median selection. Similarly, for digital input, we do 2 out of 3, that 3 inputs are taken, you take any 2 which are either 2 true false or all true or whatever. So, 2 out of 3 we take. So, this is what we do in single failure criteria. IMTBF by design redundancy manufacturing, mean time between failure has to be high. The control system should not fail, and if it is, it has to be very high, the time between the 2 failures. How do you do? By design, by having redundancy, by having manufacturing processes. You use very highly reliable systems, and suppose single control system has got a reliability of P, then you know triplicated system will have 3P square minus 2P cube, you can calculate that. So, if it is 0.99, it becomes 9972. Similarly, if you take duplicate system 1 out of 2, then it becomes 0.99 of P equal to 0.99 becomes 0.9999. So, your reliability improves. And then manufacturing process means you have to use proper cabling, twisted shielded cables, you have to provide a Faraday cage, all those things you have to take care. Design with adequate margin on critical design parameters including processing. Each system which you do must be derated. For example, simplest thing is let us say power supply. You have got a your control system needs let us say 10 ampere. So, your power supply should have a capacity to supply 20 ampere, you have 50% derating. And then what we do, we do not use single power supply, we use let us say it is 5 volt ampere, we will put 5 volt 10 ampere 2 power supplies, each will supply 5 ampere. connected with Schottky diode to the load. So that this is applying 5 ampere, this. If one power supply fails, whole 10 ampere supplied, but it is still derated condition. It is not, because rating cap is 20 ampere. So similarly, in all the components we follow that derating principle. Design a power supply with adequate availability and reliability. So I told you there are 2 power supplies, this thing. Again, in triplicated system, each will have 2 power supplies, and there will be 3 UPS, not single UPS, which will be connected to these power supplies. So suppose there are 1, 2, 3 UPS, and I have got 3 systems A, B, C. So one will get connected to A and B, 2 will connected to B and C, third will connected to C and A, and those will connected to the different main and standby power supply. So like unless all the 3 UPS fails, or unless all the power supply fails, your power control system is available. Physical separation to avoid common cause failure. Again, the 3 control systems are not kept together, they are kept in different rooms with fire barrier. So the fire in one room does not affect the other system. Also those cables which are coming from the field, from the sensors, are routed from different routes. So that fire in one route does not affect the second system. Low MTTR, low mean time to repair. Now this involves how do you achieve low mean time to repair? First thing is that you must know there is a fault, you have to identify where is the fault, and you should replace those things immediately. So to finding the fault immediately, what we call the online diagnostics, I will come back to that, and to replace it we must design in a way that it is just to pull out cards, it should not be spread, it should be immediately put, and you must have tested spares available which can be immediately placed. And since there are triplicated system, it is 2 out of 3, you can afford to switch off online one system, put it back and then do it. But we have designed a system where you do not have to switch off the power, you can directly do that. Those principles are also available. Online diagnostic and fault tolerance. Fault tolerance means triplicated system, a fault in one system does not have. But what is online diagnostics? We design our own hardware, and each hardware is designed for its online diagnostics. For example, digital input. Digital input, you will, let us say normally it is 1 or open. You will through software do a finite impulse testing to force it to close and see whether it is reading properly or not. Similarly, analog input, you have got multiplexers, you have got number of inputs, and then you test this thing whether it is giving correct output by giving one to ground and another to reference input. There are reference ICs available, a very precise voltage. So that will show it is linear and to scale. So like that, analog output you feed back and read it, digital output you see the it is a relay output, so you see the energization of coil, etc. What is that? Something is got stuck here. Okay. Protection against virus. So if something is happening, I think it is broken today. Don't worry. Doesn't leave it. Isolation protection against virus, because this is I told you we put embedded systems, not the PC based systems, and also isolation system network from plant network. So this system, whatever network we are using, has to be isolated through switches, etc. We don't use same. Display parameters to indicate current discharge equipment is like any other process industry. Recording of efficiency parameter, post event analysis, again this is similar to the process industry. Multi-level access control with privilege function, again this for security purpose. Different operator will have some level, it will be able to change some parameter like PID constant first time when he is trying to tune the system, or some parameters with which can be done by, let us say, shift charge engineer. There he has to have a key to operate, mechanical key, and also the password. When key becomes switches, when you turns the key, a particular digital input will become true, and then only he will be able to do this. Design requirements must be demonstrated to be safe and reliable with appropriate degree of confidence. I told you that we have to present our case Safety and how safety analysis of system design. How it is done? For both hardware and software, we have to prepare a document called system analysis. Now, what does it involve? It involves in each system, in each hardware, what is the failure mode? If the say board fails, what will happen? Will it affect the output? If output rotates, whether it relates the plant safety, all those things you have to present and then see that in all cases, all failure cases, the plant remains safe. So, that is what we have to do for each in hardware. And as you know, hardware's reliability can be calculated. We know each board, we take all the components in series, means any failure of any component is taken as board failure, and we know the failure rate of this. We for a particular temperature and voltage level, what is failure rate is calculated and find out the total because by forming the fault tree. So, all boards we know failure rate, then we connect make a fault tree for how they are connected in series or parallel, and then generate the reliability. So, hardware reliability you can calculate, but software reliability cannot be calculated. There is no, you cannot quantify. So, that has to be assured by how you design your software by a proper procedures. So, safe and high integrity software, which has to be I will come back how we get to that high reliability software. It should be complete, dependable and free from defects. Software integrity is assured by well defined systematic software engineering procedure, complete design documentation, version control, detailed stepwise review, concurrent verification, validation. So, verification and validation becomes important. We have to follow certain procedure. It is again coded in the Atomic Energy Regulatory Report, how we have to design the software. So, in that first we will have a document what need to be done, how to do, what functions a control system has to do. It has to be put in writing by each point by point. It should do this, it should do this every point. Then when it comes, a concept document is prepared, which will say what portion of this thing will be done on hardware, what portion will be done in software. Then hardware requirement specification is generated and software requirement specification. Hardware requirement, it will have what should be the resolution of ADC, how many bits should be there depending on the requirement and all that, and then you design the hardware. Similarly, software, and then there is a matrix is formed. Matrix says that whatever is given in design document has been put in concept document, and also all the things is covered in the software document, that is called the forward matrix. And also we do reverse matrix, that everything whatever we are doing is there, it is we are not putting anything extra, but anything extra may create a problem. So, we have to do that thing in software, and then software design, software coding, and then verification. What is verification? At every stage we have to generate a document and give to the independent committee. They will go through each thing, put questions to us, and then see that it is meeting all the requirements. If it is not there, we are supposed to do the necessary action. And the validation, what is this is the verification. What is validation? When software is completed, we have to make a full scale prototype system on which the software is loaded, and then perform all the functions, including failures. If power supply fails, what happens? If this fails, what happens? All those things, and then a complete test report has to be generated, which again need to be presented to the AERB. Now, I will take one case study which we have designed for one of the systems. Let us say for 540 megawatt Tarapur nuclear power plant. This is called dual processor hot standby process control system. It then controls various processes. Those are not important for you. Now, for this system, I had designed what is called dual processor hot standby configuration. It is not triplicated system here. Tarapur is in this thing, Maharashtra Gujarat border. It is first reactor had come there, and that was a BWR from GE company, but now this is Indian PSWRs, which is 540 megawatt. So, this supplies power to mostly Maharashtra and this thing. So, here you see these there in this DPHS configuration we have got two systems, this is system 1 and this is system 2, both are identical, and these are all the process signals which are in the form of 4 to 20 milliampere signals. They are fed to this analog boards here, analog input boards, and there are potential free contacts from hand switch, push buttons, relay outputs which also go. So, they are triplicated analog interface boards and triplicated digital interface, same is here only. So, these are the identical, does not matter. There are two microcomputers in each this thing, 1A, 1B and 2A, 2B. So, this microcomputer 1, this when through bus selector this gets connected here, second time this will get connected. So, what happens when software start, microcomputer will read all the analog and digital inputs from here, process it and generate the output, and that output is written in a dual port RAM in a some memory location. Then microcomputer 1B will through bus selector will read all input and it will also write its output to in some other location, and microcomputer 1A will read its output through dual port RAM and see whether we both are matching, outputs are matching or not. 1A, 1B outputs calculated are matching or not, and if it is not matching beyond certain limit for let us say 3 cycle software cycles, one software cycle is 100 millisecond. So, 3 software cycles it is not matching, that means the system has failed. Now, what we do, this is the digital and analog output interface. Let us say there are 20 outputs. So, 1 to 10 called X are connected here through control transfer unit 1, and 11 to 20 are connected here to another control, and here 1 to 10 are coming here and 11 to 20 are coming here. This control transfer unit is actually relay based system. Here what happens, normally this is connected here to the field actuators, to walls or whatever you want control, and they and here it is connected to this Y output. So, normally 10 output will be given by this, 10 output will be given by this. Now, if suppose we find that this system has failed because they are not matching, this gets relays get de-energized and this gets connected here. So, what will happen, the 1 to 10 and 11 to 20 all are provided by this system. So, failure of this seems is taken over by these things, otherwise both are then controlling 50-50%. If this fails, the opposite happens, this will shift here and 100% will be controlled by this. Also there is a dual Ethernet this thing, where the information is transferred to the PCBS system for all the information like any process in table, mimic, trend, history, all diagnostic message, everything comes here. So, this is the provided. So, this is 1 out of 2. So, if it is your one system has got a reliability of 0.99, this total will be 0.9999, 2p minus p square. This is the actual system which was manufactured at Electronics Corporation of India Limited, Hyderabad, and was this is there a photograph taken from ECL only, not at the plant where it is being tested. So, performance, reliability, safety and availability requirements are met by employing fault tolerant computer architecture like DPHS, using in-house developed microcomputer hardware with facility of online diagnostics, redundancy in DC power supply and AC power connections I have explained, input and output isolation for both analog and digital input up to isolation, analog input transform isolation, similarly output also transform isolation. Fail safe outputs I explained, dual redundant network, independent network with plant computer. Software development is under software quality assurance plan. I told you various stages under documents preparation and verification by independent team. Program runs under in-house developed real-time operating. We do not use any operating system from outside, no commercial. It has to be a small executive to do data acquisition, processing, output, online diagnostics in the 100 milliseconds time is designed like that. Online diagnostic promptly detects any fault in the control system and gives diagnostic message, and also it gives immediately diagnostic message on the this thing, so that if any faulty board can be replaced immediately online. The software development cycle I already told is economic requirement description, software requirement description, software design implementation, unit level. Each software has to be tested independently, then you integrate it and test it, and then after integrate software, you put in the full scale prototype system and test all the functions, all the faults and all the malfunctions, and then see it remains safe. At each stage of this cycle, appropriate document is generated and is subjected to independent review and verification. A structured and modular design approach is followed, result in software that enables a dependable and exhaustive checkout. Software verification validation techniques are used to assure a high level of software reliability. Verification by independent team, validation by using loading on the hardware, prototype hardware. Individual software modules as well as integrated system software hardware tested on the prototype system for all functional and performance requirements. The test of integrated system ensures compliance with functional, performance and interface requirements. After full testing, everything verification validation, then only it is permitted to be put in the plant. And I will tell you, in Tarapur 3-4, we had put the reactor in 2005. 2005 starting operated. Today is 22, in 17 years not a single fault in the system. So, in conclusion, in Indian nuclear power plants, the practice of design and implementation of computer systems for carrying out functions important safety has matured, and it is possible to demonstrate their fitness for the purpose. Thank you. If there are any questions, I am there to answer, whether it is for reactors or any other thing. I will try to answer.
We should salute you, sir, for the nation building such a big task. With any mistake that happens in this kind of plants will affect the generation totally, which will thousands and thousands of people will die. It's more than an aeroplane accident. Maybe few hundreds will die in aeroplane, but this is something which is beyond imagination of human race, that if something goes wrong. Many doubts we get, sir, but lack of time. One or two I will put, sir. Control systems, like you get modernization of the miniaturization of the components nowadays, especially VLSI. But when you did it in 2005, they were large in size. But don't you feel the necessity to replace them as we go up?
It is not necessary. Why? Because when you design a control system, you have to say what is response time. Now, any control systems has got mechanical components. They have certain time, few seconds. You cannot operate valve just like you cannot go from 0 to 100% open in a short time like electronics switches. It takes time. If a rod has to move, control rod has to move up and down, it has to move a certain this thing. So, there are time. For example, even this thing reactor power, if it becomes supercritical means number of neutrons generated is more than what is needed, then power will go on increasing. You have to control by controlling moving the absorber rods up and down. There also 100 millisecond cycle is enough. And when we select the components, we have to see that these components are available for long time and have been in use in the industry for very long time. Now, this whole system, control system, you know what it is based on what? Only 8086 microprocessor. 8086 the first microprocessor.
Yeah.
We have used that. Why? Because the processing power is more than enough. As far as operator information system is concerned, operator wants to see all the parameters together, diagnostic, there your PC has to be latest, and we transfer through Ethernet all the information. Every 100 millisecond it comes, because the total if your response time is 1 second, we are going 10 times faster, 100 milliseconds, and all the information is transmitted this, because operator would like to have a better graphs with how it is changing for post event analysis, everything, or diagnostic message. So, there we use latest one, but for control system we do not have that type of requirement.
But the challenges keep coming, no, sir. The efficiencies you need to increase for future or more power generation. through this?
No, power generation
fixed.
that is say suppose I want to, I will tell you here that in 220 I showed you there are 306 the tubes channels for 540 megawatt, it is 392 channels. And the same thing with the 392 channels, we are going now to 700 megawatt. Already Kagrapara 3, 4, Rajasthan 7, 8 are 700 megawatt reactors. There, what we are doing at the end of thing, some portion we are allowing boiling of D2. So that collects more heat because latent heat also gets it, and that is used to get more power. So right now the biggest reactor which India indigenous have got is 700 megawatt, which is in Kakrapara 3, 4, that is in Gujarat, and Rajasthan 7, 8, which is in Kota, and 2 are coming at Haryana, Gorakhpur 1 and 2. So these are all 700 megawatt. But we have got 1000 megawatt which are Russian reactor which have come in Kudamkulam in this thing. Those are 1000 megawatt. Those are different type PWRs, not PHWRs. India we started PHWR because PHWR needs natural uranium and heavy water, and we did not have technology of enriching the uranium. Enriching means normal uranium which you got from ore, U235 is only 0.7% and rest is U238. U230 is not fissile. It is called fertile because it gets converted into plutonium when put in reactor by absorbing neutron. But this U235 is only 0.7%. So we did not have technology that time when we started. Now we can enrich to 99% also, there is no problem. And that time also again industry was not able to support the big pressure vessel designs. Now it is able to do, and we have used in our nuclear submarine. We have designed control system for that also, not Arihant. Now 2 more are coming, which will be joining next year, Arighat and Aridhaman. Those are yet to come. So next year those 2 submarines will be coming, for which we have designed the control systems. So those are PWR type reactors, because it has to be compact.
Thank you, sir.
Thank you.
Yeah, like I wanted to ask first to my students, like how many of you knows about Bark? Homi Baba? Don't know. He's a great scientist. He worked with Einstein. He worked with Niels Bohr. Because I am very big fan to Baba. Like I used to come to teach for GATE students at Mumbai. I have seen Bark Center, sir. Due to some security issues, they were not allowed you office and like infrastructure, everything. Because I have been studying that history of Baba, then how he struggled and how he sacrificed a country. Correct, I know that because being an engineer, we need to know the great people who sacrificed their life to the India. Correct, he worked with very great scientists. Like on his name only, the Tata is funded, and he introduced that like atomic energy, and because of that, industry, because of that, Bark only our satellite technologies, all these things, even I think Vikram Sarabhai and like so many are the students of I think
actually
Baba.
Homi Bhabha was the first to start this atomic energy established in 1955,
Yes.
because he had good contact with Tatas.
Yes.
So Tata Institute of Fundamental Research
Yes,
was
exactly,
made.
right.
And because of Nehruji and
Yes.
Tata, he could make this atomic energy establishment.
Yes.
And
After that, Lal Bahadur
and
Shastri is also
even initially space
Yes.
activities were
Yes, satellite
started
technology.
there,
Yes,
then
by
got
him only.
separated as a department of space later, much later.
Right, sir, right. All
So
that.
Vikram
like,
Sarabhai was from our
Yes. Student of like I
DAE,
think.
Department of Energy, who moved to Department of Space and
Yes,
become chairman there.
Sir, is there any research is going on related to in electronics wing, because many of our students
Yes.
through
Every year there are around 100 20 to 150 students are taken in training school, BRC training school from various disciplines,
Yes.
electronics, computers, electrical, metallurgy, biology,
Yeah.
all instrumentation,
Yeah.
and all the field, and total are around 120 to 100 every year, and that is because as this was a how it was planned by Bhabha that time, that young people should be
I think in
available for R&D.
1962 he like
I think he died in 1966 in the
66,
this
right.
plane
Air India
plane crash in
crash, correct.
Switzerland.
Correct. Thank you, sir. Just I wanted to share this information to our students.
Any more questions? Any more questions, students? Thank you, sir, for sharing the knowledge on nuclear power plant and sharing the experiences. We are very fortunate to have you here, sir.
Thank you.
Thank you, sir.
I would like to move immediately. My shoes is broken because of something.
Yes, understood.
So
We'll go, sir. We'll get your
I don't.
the car and
I